welcome to this session. So my name is Jayalal Sharma and I'm a faculty at IIT Madras in the site. So I'll be speaking about a bit about complexity theory, which starts from the algorithmic problems, the programs that you've already thought about a bit, and we'll start from those examples and then we'll slowly introduce the ideas, right, that are needed in the. So it's going to be, this session is going to be more conceptual. So we'll talk about examples and then derive why we are doing certain things that we are doing, etc. Okay. So I'll start with where the sessions probably ended yesterday. So Narayan Swami must have talked about undecidability of certain problems, so you cannot write programs which solve certain computational problems, and that kind of showed us what the limit of the so-called programming paradigms are, right? So what we can program for and what we cannot program for. So we'll start with things which we can program for, and then try to see what are the difficulties that we'll face in terms of various ideas like efficiency of our programs. How much time does it take? Some programs takes longer time than some other, and how do we talk about having a good program solving a problem, etc. Right? So you must have seen some of the examples that we talked about earlier, but I'm trying to connect them together and see. Okay. So I'll start with the first 10-15 minutes. I'll take time off to actually talk about certain problems that we would like to solve, and I'll also try to motivate the problems from some of the domains that they come from, so that so then all of them are mostly going to be related to graphs in some way, so that you can connect better with it, and then we'll start from there. All right. So the starting point would be, for example, all of you have Facebook accounts, right? Anyone who's not having a Facebook account? Oh, you don't? Okay. All right. So that's usually I don't even see one hand going up. So this is rare, right? So okay. So in Facebook, you can there are these users and notion of people being friends with each other. I'm sure you know what is Facebook and what friendships are. So you can model it as a graph. Can you see how? Yeah. Right. So what are the vertices? The vertices would be users and the edges would be. Right. So when A is a friend of B, we'll put an edge, right? So this is kind of it's a social network, and we would like to understand the nature of the network in some way. For example, there is this interesting idea that this is not related to Facebook, but every individual in this world is related by 6 degrees of separation to another individual. You must have heard of this idea, right? That's an interesting idea to speak about in terms of acquaintance, right? So this person, the other person knows the next person, etc. So in 6 levels you would have reached connected any pair is what the interesting thought is. But on Facebook, what would be that number, right? So that's so Facebook also calculates this number on and off. So I think as and when more people come in, right, this degree of separation becomes smaller and smaller. I think the current number is something like 4.5 or something, right? So but they calculate it. But how do they calculate it? They actually have to process somehow some data, right, from their Facebook network and then get it. But let's not worry about that. But let's talk about the graph that captures Facebook. So is it a directed graph or an undirected graph? Undirected. Okay. Just to go further, do you know social networks where it's a directed graph? Twitter. Instagram, right? So where this notion of following, if A follows B, then B need not follow A, so that's a directed graph. So fortunately our Facebook is an undirected graph. We'll think about undirected graphs for now. So there are these big communities in Facebook where people are friends with each other and they're like very closely connected, and ideally we would like to identify big chunks of users where everyone in that set is connected to, is directly a friend of the other, right? That will be a clique. So the notion of clique is what I want to come up with. So for example, it is a natural thing to identify big cliques in the Facebook graph, right? So that's a natural question. So we'll see how it is useful in various contexts too. But here is a more precisely formulated question. You have this undirected graph, which say in this case is a Facebook graph, and you want to find out the maximum sized clique in it. So is the notion of clique clear to everyone? Should I define it? Maybe let me just write the notion. So the graph is given undirected. So graph is given. Yeah. So there is a set of vertices and there is a set of edges. Okay, and edges are tuples of vertices. And when we say graph is undirected, we say that if an edge u comma v is in E, then v comma u is also in E. Right? That's, I'm not writing it, but let me know in case there is any disconnection from what you can say. Okay, so that we can. So a subset v prime subset of v is set to form a clique. So how do you say the remaining? Right, so let me write it. So for every u v in v prime, so that symbol I hope is, so that's for all, right? For all u v in v prime, u v should be in the edge, right? So that's I just wanted to write it mathematically so that you can also think clearly, right? But idea is very clear that you want a subgraph where every vertex is directly having an edge to it and any other. So the problem that we talked about was that we are given a graph. Can we identify the maximum sized clique in it? Okay, so that's called a max clique problem. So before identifying the maximum clique, one simpler setting would be that if I give you a value k and a graph and a value k, can you check if there is a clique of size k? Okay, clique of size at least k, right? So that's so let me write that problem. So this is what we call the clique problem. So the input to the problem is a graph, undirected graph, and a value k, which is let's say that it's a natural number. So I'll write it this way, right? And the output we say is yes or no. Yes if G has a clique. Of size k, and no otherwise, of size at least k. So if it has a clique of size at least k, then it will also have a clique of size k sitting inside. Can you see that, right? If it has a clique of size k plus 1, there will be a smaller clique anyway of that, right? So size at least k is what we will write without losing much information about the problem. So the task of computing the maximum clique is one problem, but this seems to be much simpler to begin with. Can we solve this problem? Given a k, can we find out, right? Is that does the graph have a clique of size at least k? So this is what we'll talk about. This kind of problems is what we'll talk about today. So clique problem is first to start with, right? So I'm going to list down a few problems like this and talk about some of them being related to what we have seen and what you have seen at least. So clique problem, I hope the definition is clear, right? Now we want to solve this problem. We'll talk about algorithms or programs to write for this. That we'll discuss separately after I list down some more problems. Okay. So the next problem I would again like to introduce in terms of Facebook itself, right? When you log into Facebook, those who have logged into Facebook, you must have seen there are these advertisements that come on the right? It may be some iPhone, sometimes it may be soap and so on, right? So with the hope that you will see it and then you will probably click on it and buy the product and so on. That's what the hope for the advertising, the company, the soap company is, let's say, or the iPhone company is, right? And so the way they would charge is that they would charge you for, to the soap company or the iPhone company, what they'll charge is they'll charge the Facebook will say that, okay, you have to pay me 1 rupee or 5 rupees, let's say, to be reasonable, 5 rupee per user that you are advertising to. Okay, so if I am the iPhone company owner and I would want to decide which all users I want to advertise to, right? So that I can reach out the maximum and so on. So I have different strategies. So let me just discuss one of the strategies that we will see. So the hope is that if I advertise to one user and get him or her buy the product, the hope is that his or her friend will hear from him or her, and buy the product as well, right? So if I have two people who are friends with each other, maybe I will probably advertise to only one of them. I'll probably not advertise to the second, because I'm hoping that the first one will get convinced by the advertisement, and through the friendship the second person will get to know about it and buy the product. So I don't need to waste my 5 rupee for the second person, right? This is what the hope is. Okay. So with this strategy, so the company gave me the directive that, okay, look, you have to choose the users in such a way that you reach out the maximum but do not waste any rupee. Meaning that if two people are friends, don't ever advertise to both of them. Okay, so that's one constraint, and you choose the maximum number of users that there's no limit on funding, but no wastage of money. That's the strategy that the company has given me. So the iPhone company will say that, okay, look, I'm going to choose a set of users to advertise to. What will be the constraint that they say? The set of users will be such that between any two users whom I decide to advertise, there should not be an edge between them, right? That's my constraint, and I will choose the maximum size sets this way. So let's define that set mathematically a bit. So this so a set V prime subset of V is what we are choosing, okay, as to advertise to, such that what I want is that between any pair of vertices in the set that I chose to advertise to, the set of users that I chose to advertise to, there should not be an edge, because if there is an edge, then I am actually wasting money by advertising to both of them. And I want this V prime to be as big as possible, so that I actually reach out to the maximum set in the Facebook graph. So this is with the very conservative approach that I don't want to waste any money, right? I don't want to waste any money. So this set has a name. V prime says that for every UV there is no edge in the among the vertices. This has a name. Do you already know about it? It's called an independent set. Sorry, yeah. Independent set, right? So this is what, so V prime is called an independent set. Okay, so right. Now, so again, the computational question related to this example is that you are given the graph and you want to find the maximum sized independent set, because I want to advertise to those set of users, right? So let me write that. That is a problem called independent set problem. So let me call it in set problem. So I am going to simplify the problem in the following way: G and K are given, and output yes if G has an independent set of size at least K and no otherwise. Okay, that's the independent set problem. So I am going to talk about one more cousin problem of this, where I am going to change my advertisement strategy. Okay, the strategy by which we will advertise from now on. So are there questions about the click problem and independent set problem before we go into the next example? Very good. So we'll actually come to that, right? So that's the reason I actually wanted to write them side by side. Okay, good. So you already observed it. So we actually come to that relation that was observed right now. So we'll come to that soon enough. Okay. So in fact, yeah, it's very clear that in E and not E are actually written side by side. But it's a good observation to make, right? So we'll come to that. So let me talk about the cousin problem, right? The next cousin problem, which is change in the advertisement strategy, which is that from now on the company realized that their product is not being sold well, right? Maybe because they have this conservative advertisement strategy. So they changed the strategy, saying that, okay, look, I allow you to waste money. You can advertise to friends from now on if you want, but guarantee me that every friendship in Facebook, right, will be hit with your advertisement. Meaning that if there is two people are friends in Facebook, you should advertise to one of them for sure. So that's like, I'm going to flood Facebook, right, with my, but that involves a lot of money. But still, I'm worried about my product not being sold enough. Okay.
In this case, the idea is that every user will visit it or will take care about the product.
Yeah, so that is one way of doing it, right? So you can actually talk about, you can advertise to every user, and then your product will be, so every friendship will be hit, right? But maybe we can do better. So is there a better way of doing it? So let me define mathematically what would be the subset of users that you would want to advertise to, right? So you would want to advertise to a V prime subset of V, right, such that, can you complete the condition? So I want a subset of vertices to advertise to such that every friendship is hit.
Size of V prime is least, and what size of V prime should be least.
Size of V prime should be least, correct. So one V prime that we could choose is V prime equal to V, but that is not interesting. We actually would want to do better, right? So what would be the it would be an independent set, meaning that you may not hit any all friends.
Like for every edge, one of the vertices must be inside V prime.
Right. So let me capture that definition, right? So for every edge E, which I will denote by U comma V in E, either U should be in V prime or V should be in V prime. Okay. Or both.
But it's and or.
Yeah, so it could be both, we don't mind both being there, because our company allowed us to wastage of money also, but their aim was to flood, right, to make sure that, right. So this subset has a name. Anyone know about this name?
Vertex.
It's called a vertex cover, right. So V prime is called a vertex cover. Now, are we interested in the maximum sized vertex cover? The minimum sized vertex cover, different from independent set. In the case of independent set, we were interested in a maximum sized independent set. Here we are actually interested in the minimum size vertex cover. So the input, let me write the input now. The input is, again, I'm going to write it in the form of a G and a K, okay, and output is yes if G has a vertex cover. I'll write it as VC of size at most K, okay, and no otherwise. Okay, so this, I'm interested in finding the minimum sized vertex cover. So I'm interested in finding that K such that this answer is yes. The least K such that this answer is yes. Okay, so I hope you can relate to all these three problems, and they are variants of each other, just minor changes, and the examples that I said from Facebook, right, are partially made up just to relate to them, but I hope the problems are related to what you have seen. Okay. So the fourth problem that I will talk about, okay, I have 5 problems actually, so I'll write the fourth problem also. So the fourth problem is more familiar to you, so I probably don't need an example to talk about, but still I will talk about an example, at least in my favorite way, right? So you must have played this in your cartoon books, where at the back side there will be a diagram which has a rabbit and a carrot, right? Rabbit will be in one corner of the diagram. There will be like a complicated diagram that will be where with some blockages and passages and so on, and at the other end there will be a carrot given, and you are supposed to show the rabbit the way to go to the carrot, right? So what problem are we solving? Yeah, it's the reachability problem. So we actually are modeling the problem as a graph, right, by putting vertices appropriately according to the diagram, and whenever there is a blockage we will not put the edge. Whenever there is the passage opened, we will actually put an edge, and we are talking about, is the the rabbit vertex, right, the carrot vertex, is it reachable from the rabbit vertex? If so, show a path, right? So it's reachability. We are not worried about doing it in the shortest way, so it's not shortest path, but still it's a reachability problem. So that's what I am going to write as the next problem. So the input, what should be my input? Forgetting about the rabbit and the carrot and so on. You have the graph, right? Let's a source and a destination. Undirected, so G is undirected. Let's say in this case, the normally it's undirected. You can go one way, the other. So graph is undirected, so G is undirected, and S and T are in the vertex set V. Okay, and the output is expected to be yes if I will write it this way: S to T. There is a path in the graph G. I hope the notation is okay, right? And no otherwise. All right. Right. Okay. So I'll introduce the next problem also. So that the fifth one, and then we'll talk about the algorithm. So are there questions about this? I'll just let me name them. So I didn't write the names. So this is the vertex cover problem. So it's VC, and this is the reachability problem. All right, okay. So now the fifth problem that I would want to talk about is a little more engineering oriented. So let me just introduce the problem slowly to you, right? So okay, so I'm not sure how much you are exposed to this, but let me just start on by drawing a diagram. So, so we are going to talk about functions, okay, which take n bits and outputs 1 bit. Okay, so they are Boolean functions. They are called Boolean functions. And we want to, so normally when we design circuits which work, for example, the one which works in the mobile phones and whatnot, so there is a circuit design for a given function that is involved. Okay, so there is a hardware engineer who actually wants to design the circuits. Okay, so he comes up with a circuit which computes. So there is a particular Boolean function that he's asked to design a circuit for. He comes up with a circuit C. So what do you mean by circuit? So circuit actually has these gates called AND and OR gates. Okay, so let me draw the gates. For example, this is an AND gate and this is an OR gate, and they are connected with each other. So there is this x1, x2, x3 and x4. So these are 4 bits, 4-bit function, and value of n in this example is 4. Okay, 4-bit function. It produces an output, 1-bit output. And the hardware engineer came up with this circuit for the example function that he had, where n equal to 4. Okay.
So these circuits could be of any type, right?
Could be of any height, yeah, any depth. And so we are interested in optimizing on the circuit. But how do they compute the function? Is that clear to you? For example, if I give you values for x1, x2, x3, x4, you can compute what the AND value would be. AND of 2, the zeros will be 0, AND of 1 and a 0 will be 0. So there is a particular way in which AND gates behave and so on. Okay, so finally you can compute what the output, the top gate computes, and that's the Boolean function supposed to be. Okay, so this hardware engineer came up with the circuit C. Okay, and what we are interested in doing is that we are interested in optimizing the circuit C in terms of the number of gates used, because that's what actually is going to be determining how much size it require, space it require, and integrating it into a mobile phone, etc. Right? So you actually are interested in optimizing the size of the circuit. What is the size? The number of gates. That's what we'll talk about. Okay? So size, number of gates. So what the hardware engineer came up with is an example circuit, but his manager tells him that no, you should try to optimize it better. Is it possible to get a better circuit? Better in terms of what? Number of gates again. For example, is it possible that you can have a 2-gate circuit for this particular one, right? This has three gates. Can you do better? So what can the engineer do? He can come, sit and think about, is there a way to optimize and so on. Yeah.
Yeah. So are the circuits only composed of AND and OR?
Correct. Yeah. So I drew the example like that. You can also use NOT gates.
Yeah.
So and or and not. Let's fix that example. But the problem that I'm going to talk about is not relevant or would not change if we fix it separately. Okay. But it is important that we are talking about one particular set of gates with which you are designing. Okay. So this is what the task is. Can you optimize it better? So here is a problem that a hardware engineer is interested in solving. So he has a circuit that he came up with. Okay. He has a circuit that he came up with. He would want a program that we write for him such that the program should tell him yes or no. So what does yes? Yes is when C is the best circuit for its function. So what do we mean by its function? C computes a function. Its function, can you do better at all? Okay, and no otherwise. So what the engineer would like is that he would like a program that we write for him such that he can design a circuit and give it to this program that we are writing such that our program will tell him whether it's optimal or not. Otherwise, how can he determine, right? There is no other easy way that he can determine whether he has already hit the best or is there some more optimization that he can do.
In this case, the best circuit would be the circuit with the least number of operations, right? Like the least number.
Yeah, so the best in terms of we're measuring in terms of the number of gates used in the circuit. That's the size. That's what we'll always measure it as, right? So in this case, we will be interested in knowing are there circuits of 2 gates in it and so on. Okay. So that's the optimization that we are looking for. So he is trying to optimize it, but the input output for the problem that he is interested in for us to program for him is this. He will design a circuit and give it to us, and then we have to check whether it is actually the best circuit for its function or not. That's what the task is. Okay. So this, let me name this problem. This is called a min circuit problem. Okay. Are there questions about it? This is probably the most far away problem from what you have seen, but let me. It's 3, correct. It's 3.
So can you give an example with real Boolean values?
What do you mean by real Boolean values? So let me draw this circuit. Let me draw the corresponding function for you. Right? The function has 4 bits. This x1 to x4 is the n is 4. That means the function should be defined for all the possible combinations of these 4 bits. So I should actually draw the 0 0 0 0. What should be the function value? 0 0 0 1. What should be the function value? Let's do a few examples. Right? So in the first case, what should be the function value? 0, because AND of x1 and x2 would be 0. Right? So and the AND of x3 and x4. So the first one it would be 0, and the second one 0 again. So you can see that this function will be 1. For example, 0 0 1 1. This function will be 1. You can see that, right? So that's how this is what we mean by the function corresponding to the circuit. So you're given a circuit, and for a circuit there is a function associated with it. But interestingly, in our design question, the function is given to us. Okay, and the engineer is supposed to come up with a circuit which computes that function. Okay. And he is interested in knowing whether his circuit is actually the optimal. That is the problem that we are talking about. So his problem is this. I mean, he designed a circuit. He wants to know whether it is actually the smallest circuit. So he wants us to write a program for him. Okay. So we have advertising agencies approaching us. We have hardware engineers approaching us to write programs for these problems. So all these problems have a peculiarity. They have some input given to us, and the answer is supposed to be yes or no based on some properties. Okay. So we have actually defined the 5 problems. Let me just write them in one go. So we talked about the clique, we talked about the inset, we talked about vertex cover, reach, and we talked about the min circuit. Okay, these are only representative ones. There are many more problems that we would like to solve and so on. What we are interested in understanding is, how do we go about talking about writing programs for them, which means you have to design methods, algorithms for solving them, and what are the limits that we will see, and how do we address the limits, etc. That's what the next point of discussion would be. Okay, is that fine? Are there other questions? Okay. So which one of these you can start with designing an algorithm? Reachability, that's very good. So reachability is something that you have seen, right? How do you go about writing a program for reachability? Depth first search and so on. So whenever we design a algorithm or write a program for these, we would actually want to understand how efficient they are in terms of. So then the question comes, how do you measure the efficiency? Are you already aware of some ways of measuring efficiency? Asymptotics, running time of an algorithm is what we should look at, and running time is measured in terms of what? So it is actually an interesting question. I have a reachability program which solves reachability. I have an input to reachability, and the program will tell me yes or no. It runs for some time. How do you measure the time? Now, how do you compare two algorithms which solves reachability? How do you understand that the first one is better than the second? Yeah, so the measurement of the running time of the algorithm, in fact not even running time, the resources of computation that it uses will always measure in terms of the size of the input. Why is that done is questionable, but that we will not, that's beyond the scope actually for the discussion right now. Okay, we'll take it as the size of the input is what we measure it in terms of. All right. So
input in terms of number of bits.
Correct. So then actually the next natural question comes. When I say size of the input, I should fix how is the input given to me. For example, the reachability question. Right, reachability question, you can, how is the input going to be given to me? So you said a graph is given to me and an integer k is given to me. Sorry, s and t are given to me, not k. And in s and t are given, g and s and t. How is the graph going to be represented? So we know that a graph can be given as a matrix, right? With the ijth entry will be 1 if there is an edge from the, right. So let's worry about adjacency matrix right now. There is also adjacency list representation, which also applies to the discussion that we are talking about in similar way, right? So what would be so for example, in the reachability problem, let me go back to it, just to G, S and T are given to me. So suppose that the graph has n vertices, okay, n vertices, and we can without loss of generality assume that S is 1 and T is n. That's only a matter of renaming the vertices, correct? No? So you can just assume that that's the way it is given, right? And then the graph is the real input to us. The graph is the real input. And how is the graph given? The graph is given in the form of a matrix. So what is the input size for us? How much, if the graph has n vertices, how many bits are given to us? N square bits are given to us, okay? So that's a real, so really the input size is n square at this moment. But let's not worry about that too much, but at least in terms of n, I want to stress the point that whenever we say the running time is measured in terms of the input, we should actually think about what is the input representation. That was the reason for the discussion, okay? So reachability, we know several algorithms. In fact, one of them is what you suggested, the DFS or BFS. So let me write the running time of that algorithm in terms of the input size. Are you already aware of the analysis? So it is order V plus E. Correct. So it actually varies with that respect. So okay, what is the worst so maybe let me write it as n square. Order n square, is that good? So when n is the number of vertices in the graph. Okay, n is the number of vertices in the graph, so order n square algorithm you already know. In fact, this is actually a reasonably fast algorithm because as you will see, you will actually get the other problems in this list are actually worse off in terms of designing algorithms. We will actually talk about discuss that right away. But what kind of algorithms are we looking for? Okay, so let me also fix that at the moment. So this is the notion of what is the notion of efficiency. So we are looking for algorithms which run in the following running time n to the k, where k is a fixed number which should not change with n, right? So order n to the k time. So in that sense, reachability is good because the k value of k here is 2. Okay, so we would not mind reachability being solved in order n cube time also because the value of k then would be 3. But again, the question is, why is this the notion of efficiency, why not something else? That is slightly beyond the scope right now, but we will discuss that. Yeah.
This is called polynomial time.
Yeah, so I am going to, so this running time is what's called a polynomial time. So let me call the polynomial time. Why is it called a polynomial time? Because this expression looks like a polynomial in n, right? So this expression looks like a polynomial in n, and what is n here? N is the size of the input technically. So we'll, for the graph problems, we'll kind of take it as n is the number of vertices. Size of the input is actually n square, but let's not worry about that, disparity right now. All right. So that's a story of reachability in this list. Let's actually attempt on the other ones. So Clique, for example, Clique independent set vertex cover. We'll try out the other examples quickly, right? So let me go to the Clique problem. You're given a G and a K. Okay, G has, let's say, n vertices, small n number of vertices, and K is an integer that is given to you. K could be n by 2, for example, right? I might give you n vertex graph and K could be n by 2. And you're supposed to check whether G has a clique of size K. What is the most trivial method that you will think of? Try out all possible subsets of size K and check whether they form a clique or not, right? So then that's a very simple algorithm to try out with. What's the running time of that algorithm? N choose K, then there is some multipliers which will actually be corresponding to the time that you require to check out whether a given subset forms a clique or not, right? Right. So K choose 2, right? N choose K times K choose 2 or something, roughly like that. But N choose K is actually the most important parameter there. So let me write that one here. So N choose K is the most dominating running time there, where K is like N by 2. It can be like N by 2. The user can actually give you. So this will actually be right like n choose n by 2, and that would be 2 power, right? So order n. So let me write it as exponential in n. Now it is not like it is off the, so when I say exponential in n, I'm sure you might have seen it, but let me write it. It might be of like this kind. It is not going to be of the kind n power k. So that algorithm that we designed is the trivial algorithm, but we would like to do better. Okay, so especially given that this problem is kind of quite important and critical, right? Not just this, in fact the other ones are also critical. So we would want to try out what are the possible algorithms that you can write for the other ones as well. So what do you think about independent set and vertex cover?
Independent set is related.
Independent set also you can probably solve in the same way, that is possible, right? So you could do DFS from each.
Or BFS from each node.
DFS from each node.
So all the neighbors of a node we won't count in the set.
Right.
And like all the odd, also we won't count all the neighbors and we'll count everything else.
But will we miss any vertex that could be in the independent set? That actually is a good idea, but it actually works only in certain kinds of graphs. But we can produce, in general, we can produce a counterexample for that approach, even the DFS approach. But I think it's good to start with such attempts and try to find out counterexamples why it wouldn't work. For example, the approach that you suggested, the dynamic programming one, will actually work if the graph is a tree, if there is no cycle. Okay, but otherwise we can produce counterexamples. But anyway, it's a nice approach to start with, right? But I hope everyone is clear about the trivial algorithm at least, that all these three problems actually you can solve in a similar way. They are all trivial algorithms, but they don't give us any better running time than this. So it doesn't say anything about that there cannot be a better algorithm. It just says that look, the algorithm that we tried are not good enough. That's it. So you're always in the quest of better algorithms in this case. We would want to design better and better algorithms, okay? Let me talk about the unfamiliar problem for you, the min circuit. Let me write down the algorithm for the min circuit, the trivial algorithm. So how will you go about writing an algorithm? No, don't worry about its efficiency, because as you must have understood yesterday, even having an algorithm for some problem is a big deal, because there are problems where we can't even write algorithms for which actually always gives us an answer. So in this case, let's write down an algorithm which is in the trivial, in our mind, very trivial. So what is our input? Our input is this circuit that the hardware designer designed. So it looks like this. It looks like this one. Okay, is the pointer coming there? Yeah. Okay. Right. So it looks like this. It meant this is only an example, but in general you are given a complicated circuit. Maybe there are 1000 gates, right? And you want to actually find out whether that's the optimal circuit or not. How would you go about doing it? Yeah, you want to know whether it's the best circuit. So what you would try is,
all smaller circuits.
very good. So you actually look at smaller circuits, right? And for each of the smaller circuits, you would want to check whether
It matches the function.
it matches with the function. How will you check whether it matches with the function?
2 raised to n.
Yeah, so you actually run over all the rows of the truth table, that table which actually has the values, and check whether both circuits are evaluating to the same. So let me write this. So we just talked about it. Let me write this. So given a circuit C, run through all C primes smaller than C, check if for every x in 0, 1 power n, so I hope that makes sense, because we are running over all possible inputs, whether Cx, C prime x is equal to Cx. Okay? If C prime x is equal to Cx, then that means that C prime is computing the same function as C, and you have found a smaller circuit. And if yes, so I'll then output no. And if the loop exits without finding a smaller circuit C prime, you can output yes. All right. This is what the trivial algorithm for the problem is. Okay, I realize that some things that I am writing is getting cut off, but I hope, so yeah, I will not use the left corner then.
Sir, in this problem, what is given as input?
The circuit C, yeah, good question. So I actually wanted to come to that. How is the circuit given to me? Right, circuit is given to me. So what is this, the input is a circuit C, the circuit that the hardware designer designed for the function that he was given from his manager. So he was given a function f, he designed a circuit, manager was not happy about it. Manager said, okay, why don't you go and design a better circuit, but he doesn't know whether there is a better circuit. So he would want to use our program to check whether his circuit is. That function could be anything. It's not important that what, so it's some function that was coming up as a part of the work. So it's some arbitrary Boolean function that was given to us. It's a truth table, let's say, right? And not to us, to the engineer. Engineer came up with a circuit C. He wanted to know whether it's optimal. So the input to our program is a circuit C that the engineer designed. Now output should be to the help the engineer whether it's the optimal one or is there a smaller circuit. Okay, that's what the program is checking.
So in this circuit, every x1, x2, every x gives input to only one side of a
Gate, no, it need not be. I could actually have a edge like this, right? So it could be complicated like that, right? You cannot think of it as a directed graph from bottom to top, right? It's a directed acyclic graph in some way, right? That's the, so this algorithm, do you think it's, what could be the running time? When I say running time in terms of input size, how is the input given?
Maybe more than exponential.
The size, the circuit is given to you as a directed acyclic graph, and there are n input bits, let's say. So let's write down the algorithm in terms of n. Okay, so clearly it's going to be exponential because inside the loop itself we are actually going through all x's in 0, 1 power n. That means it's going to be exponential time anyway there, right? And there is also this outer loop which actually runs through all circuits. So it's actually going to be even worse. So let me write it as, it's going to be at least,
Might be something like 2 raised to n square or something.
right, so it's going to be exponential in n square. That's correct, but let's not worry about whether it's n or n square because exponential is bad for us. So there is this question.
Are the operators just binary operators or?
Just binary operators. For now, let's think about them as and, or, and not gate. That's it.
Like we can't have 3 edges from the and.
Oh, you mean whether the operators are binary? Okay, you can have arbitrary edges also, but that wouldn't simplify the problem much, right? And whether you have restricted to 2 or not wouldn't simplify, because we are trying to design a better algorithm than this. If the circuit was known to be binary always, I mean each gate is binary, it is not clear how a better algorithm can be designed. This algorithm is oblivious to the fact that whether it's binary or not, right? But in general, it need not be binary. It could actually have any number of inputs to an OR gate.
So in our example, an AND gate can have arbitrary number edges, OR gate can have arbitrary number edges.
Arbitrary number of edges.
Negation has only one edge.
Negation has always one edge, right? That's because negation is a unary operator anyway, right? So that's is that clear? So good that we are asking questions, because that's one unfamiliar example for you. So you probably can. So this is already a bad algorithm, but it's a trivial algorithm. We would like to design better algorithms to help our hardware engineer to figure out. Okay. So this is what the scenario is. We have these problems. So these are representative problems, some of them actually yielded to our algorithmic attempts. Some of them do not, or not yet. Right? We would like to have better and better algorithms. This is the situation. Okay. Okay. Good. So now let me talk about. So how do we go about? People have attempted, and several attempts have been made to actually improve this, the solve clique independent set vertex covered using various algorithmic strategies that we know of, etc. Right? But most of them seem to fail, or rather, we can actually find counterexamples to them. But so what could be the reason? How do we go about understanding these problems? So I am going to draw the diagram. So there is a set of problems for which we know a polynomial time algorithm. Let's name that class as P. Okay, so what is P? P is a set of problems like this, right, where we know polynomial time algorithms solving them, and then there are these problems outside P. What are the example problems outside P? So clique, inset, VC, min circuit. Outside, when I say outside P, that is mean at the moment we do not know a polynomial time algorithm for them. We are not putting it outside for permanently. And one problem that we got into P right now is reach, because we knew DFS based algorithm. Okay, so we would want to understand the properties about these world outside, because that's where most of our interesting problems are in. How do we go about designing algorithms for them and so on? Since we failed so many times, it actually makes sense to step back and ask, what is the structural difference? Is there any difference between clique and min circuit problem? Is there any relationship between clique and independent set problem? Right? Differences and relationships we would want to understand, right? So is there any distinguishing feature that, let's say, clique and independent set has, which we could exploit to actually design a polynomial time algorithm so that they fall into P? This is a dream, right? So we would want to look for properties that these ones have and connections these ones have. One connection is something that we already observed in the beginning. There is a connection between independence and clique in the very way it was defined. We'll come to that. That connection we'll actually exploit soon. But before that, let me actually understand the differences between them. Okay. So I actually want to say that there is a difference between the min circuit problem and the clique independent set vertex cover problems. That's the reason why we wrote it separately in 2 columns, so that we can distinguish between them. Okay. So let us understand the difference. So here is one peculiar nature that clique independent set and vertex cover have. Okay. So here is one way to think about it. Suppose if you are given, let me remind you about the problem, clique independent set and vertex cover problem, and suppose that you are given the input to these problems. So let's say G and K is given, and G and K walks through the door, and I claim that there is a clique of size K. In the clique problem is what I am talking about. I claim that there is a clique of size K. I don't tell you, I claim, I jump and say, oh look, this is a yes instance, this answer is yes for this instance. But you don't believe me, okay? So you ask me, okay, convince me. So how will I convince you that it's indeed a yes answer for this problem?
You can show a set of vertices.
Right, so I could just simply show you the set of vertices which forms a clique, right? Then the job is very easy for you. You can just look at that set of vertices, right, and check whether it forms a clique or not. And if the answer to the question is no, then there is no way that I can convince you by giving a subset. You will catch me when you check for a clique. If the answer was no, I will not be able to convince you, right? So this problem, clique problem, has this peculiarity. Yes instance to the problem has a very simple way of convincing the user about yes instance property. Let me say it is called a certificate, right? It's called a certificate of the yes instances have a certificate which has the property that it can be verified easily, because once I give you the set, it's very easy for you to check, right, whether it actually is a clique or not. And second, it is actually short, meaning I can write it in a very small. So how will I give you the subset of vertices? I will just say, oh, this is vertex. You just check that, right? That's what. So that's an easy way of representing. So the peculiarity that clique problem has is that yes instance of the problem has a short, easily verifiable certificate, and no instance doesn't have that. Okay, that's the and let's check whether independent set also has that. Very simple, right? G and K are given to you. If I claim that it's a yes instance, I can just show you the independent set. Okay, and you can verify whether it's an independent set, and it's a very short and easily verifiable certificate for it. Vertex cover problem also has that property. Same. How about reachability?
Yeah.
That also has, right? Reachability also has. Why? Because for a graph G and S and T given, if I claim that ST is reachable from S, I can actually show you the path. So you don't need to search for the path using DFS and so on. You can just check whether the path is correct or not.
But you could even have an empty certificate, right? The guy can just, the verifier can just run the reachability algorithm.
Correct. So the point that he's raising is that, oh, in this case you don't seem to need the help of me to actually figure out whether it's a yes instance or a no instance. But that's a peculiarity to this problem because it is actually already efficiently solvable. Correct, no? But the point I want to say is that conceptually all these four problems seem to have this property that yes instances have a very short, easily verifiable certificate. Now let's look at the fifth example friend, the min circuit problem.
How can we assure that it is the minimum vertex cover?
No. So the problem that we are talking about here is not the minimization version. It is given G and K, whether G has a vertex cover of size at most K. So it's not the minimization version. We are using the fact that we are talking about the decision version of the problem. Correct? Yeah. So that's the right. Okay. Any other questions about the first four problems? It's fine. Now here is the fifth problem. Fifth problem, let's try out the certificate issue. So the engineer gives us a circuit C, and I jump and say, oh no, the answer is yes. It is the best circuit. You are not convinced. You will ask me, okay, how do you say that? Right? Is there any easy way that I can convince you? I can convince you that what came through is the best circuit. So if you think about it, right? So best circuit that I can give you is, I don't know how to convince you by giving one circuit, right? I can convince that it is a no answer by giving a better circuit. That I can convince you, right? That is possible. But how will I convince you that it's a best circuit at all? But even if I give you a circuit and say that it's a no answer, how will you verify that circuit? You have to run through all possible inputs and check whether it actually evaluates as the same. That again is not an easy algorithm. It actually runs in exponential time. So this problem has the difficulty that one, it doesn't even have the easy certificate to give. Even it has an easy certificate to give for the no answer, not for the yes answer. Even if I give the easy certificate for the no answer, it is not easily verifiable, because to verify my certificate you have to run through all possible inputs and check whether C of x equal to C prime x. So it actually is not fitting the bill in both senses, right? So it seems to be standing out. So all these four problems were ones which we wanted to solve, but this one seemed to have a peculiarity which these three doesn't have, or these three has a peculiarity which this one doesn't have. So what we would ideally want is to exploit that peculiarity that these three problems have. What is the peculiarity? Their yes instances have an easily verifiable short certificates. That peculiarity we would want to exploit and design good algorithms for them. The advantage of approaching problems like that rather than attacking one problem at a time is that you actually pull down a bunch of problems together. right? You actually, if I use just the property that there is a yes instances have a easily verifiable certificate to design the algorithm, the advantage is that any other problem that you come up with in future, if it has the property that we are talking about, the easily verifiable certificate for yes instance, it will also fall down to P, right? Yeah. Not really, but maybe there is a notion randomized algorithm which is slightly different from, but that is not actually within this discussion regime. We'll probably take it offline, right? But I just wanted to say that, but is everyone with me on the distinction why we want to distinguish between them? Yeah.
Certificate of minimum circuit problem again?
No, so yes certificate doesn't exist, that's what the point. So minimum circuit size, there is no certificate for that I can give, which is short. Right? That's what so it's a negative answer that we gave. We said that look, for the minimum circuit problem, I don't seem to have a very small circuit that I can give, very easy way of convincing you that what came through was the best circuit. Whereas the clique independent set vertex cover has that property. So that's the distinguishing feature. So these three, we are hoping that because they have that feature, they may fall down to P. Okay? Now interestingly, let's collect all these problems, all the problems which has this feature. The yes instances have easily verifiable certificate. Let me draw that circle here. So here is why did I draw, reach was also inside it. Okay, reach was also inside it. I actually claim that every problem which you can solve in polynomial time are also going to be in this. Because if you can solve, then you don't really need my certificate, like the way we observed in the reachability case, right? So that's why this was drawn like this. And this class of problems which actually has this yes instances have this easily verifiable short certificate, right? There is some informal nature of the definition. I'm not putting down the formal definition, but still this is the spirit of the definition. This class is what is called NP, and it's named non-deterministic polynomial time. Why non-deterministic? Because it has some connections to non-deterministic Turing machines, right, some of which might have been discussed yesterday, but I would leave it at that, right. But the interesting idea is that we are trying to capture those problems for which the yes instances, those decision problems for which the yes instances have a short easily verifiable certificates, and no instances will be caught in the certificates will be caught. So this is the distinction that we are trying to make between these problems, all right. So the min circuit is still outside. So that is so ideally we would want to show that every problem in NP is in P. Why? That will show that any problem that you come up with in the future, if it has this yes instance being easily verifiable certificate, it will be in NP and it will fall down to P. So this actually brings to this famous question, is every problem in NP also in P? Okay, so this is the famous P versus NP question, and you must have heard about it informally or otherwise, right? So this is the intuitive content of that question. Okay, so we identified the set of problems, and so it's a conceptual development that we are doing, right? And the advantage is that we are not trying to be very problem specific. We actually are trying to be structure specific of the problem, so that any problem with that structure will fall into a framework. So this way of classifying problems and based on their structure, right, than the individual nature of the and trying to understand the relationship is what starts off with this basis of what is called a complexity theory. Okay, yeah.
Are there any prompts that you do to be like outside NP, like sort of on the very outside?
Yes, for example, the halting problem that you talked about yesterday, that anyway doesn't even have an algorithm. So forget about NP.
Are there any prompts which have algorithm but it's not in NP, proven not to be in NP?
There are actually, there are even practically relevant problems which are outside NP. Min circuit, we unfortunately don't know whether it's in NP. What we said was that we cannot think of an easy certificate, correct, no? But there may be a complicated way of coming up with a certificate, we never know, we haven't disproved it yet. That means that min circuit could potentially fall into NP, we don't know that, okay? So that's a scenario, right? Is everyone clear so far? So in the next 15 minutes, I'm going to tell you something interesting in the complexity theory scenario, which is trying to understand this further in terms of the conceptual ideas, okay? Okay, I'll wait for questions in case there are any, because this is a...
So where is min circuit?
Sorry?
So where is min circuit placed?
So even when I say click here, I drew click here, but I don't know whether it's here, maybe it actually falls. We don't know that, right? Just that I drew it here because that's the best algorithm that we know of. Min circuit, I drew it here because that's the best algorithm that we know of, or that's the best way that you know of. We potentially can in future somebody could come up with an algorithm for min circuit and put it into NP or even in P. We never know. So it's kind of unsettled in that way. In fact, all these problems in that way is unsettled.
Sir, could you explain the relation between the largest click and the insect problem?
That's what I'm going to come to next. The observation that we made, right? That's the point about the right. Okay. So now let's get to the next idea, which is the comparison between problems in NP. Okay, so we have these problems that we talked about, 3 problems in our picture: click, independent set, in vertex cover, and even reach. All of them are in NP. Okay, so one thing that we actually try to understand is what is the difference between the problems that were outside NP. Now we are going to understand what is the similarity between them, or what is the connections between them. Can we actually solve independent set problem if you had an algorithm for solving click problem, or the other way? Right, that's what we are trying to understand now. So let me formulate the task in hand using this box. So I have this box. Okay, maybe I'll draw it slightly differently. So I have this box which is claimed to solve click.
So this is a black box. I don't know what to make.
Correct. So click algorithm. So click solver. Let me call it the click solver. Okay, click solver. We don't know how it is done. We are hypothetically assume that suppose I manage to find a very good algorithm for click. Okay. So what is the input to this click solver? What is the normally that we will give? We will give a G and a K, and this is supposed to tell us yes or no, depending on whether G has a click of size. K or not. Okay, and no otherwise. This is what the promised behavior of that program is. So this box is a program. Yeah.
We can assume that the graph is a matrix for that.
Yes, we can assume that. So that is always throughout the assumption. We actually are going to represent graphs using only adjacency matrices. The discussion also applies when it is adjacency list, but some slight change in complexity will be there. But it's only a matter of order n square versus order n cube. But the regime that we are talking about is not there, right? It actually is exponential versus polynomial. So it's not. So this is what the click solver that is promised to be. So we are given a box which has a program which is claimed to solve click. Let's say that it runs in polynomial time. It's hypothetical, right? What we want to use it for, to use independent set problem. Okay, we want to use this click solver to solve independent set problem. So what is our input? Our input is another G and K. Right, and we are interested in not solving the click problem. Oh, I think I am writing into the. So we are writing we are given G and a K. We are not interested in solving the click problem for G and K. We are interested in solving the independent set problem for G and K. So I want to use this click solver as a subroutine, or as a function, and I want to invoke it and get the answer. But the problem is that I should not use G and K as it is as the argument for the function, because that wouldn't make sense, because we want to solve independent set problem for G and K. Why would we use click solver for directly for that? We should carefully modify G and K and produce a G prime and a K prime, right? Produce a G prime and a K prime in such a way that the answer from click solver for G prime and K prime will help me to give the answer for independent set about G and K. This is what the connection that we would like to make. Okay, so let me solve that, make that box as follows. So I want to draw this bigger box, which we should call inset solver. So there is a click solver that is promised to be ready for us. Our aim is to build this independent set solver using that as a subroutine inside. So what we should do is that we should take this G and K and modify it to get a G prime and a K prime. Right? So let us use the observation that we made earlier. In fact, one of you already made it, that if you have a G has a click of size k, then you consider the graph G bar. What would be G bar? G bar is the complement of the graph. Whenever you have an edge in the original graph, you remove it and place it, remove it in the graph G bar, and whenever you don't have an edge in the original graph, you place it in G bar, right? So it's a complement graph G bar. So what will a clique look like in G bar? A clique in G will look like an independent set in G bar, because all the edges would have been removed by the complementation, right? So G has a clique of size k if and only if G prime has and G complement has an independent set of size k, right? So this is what we want to use as a critical property for designing this bigger box. So what you should really do is that you should produce G prime. Our G prime in the diagram, the input that we give to the clique solver should really be G complement. You take G and take the G complement. So you know give it to the algorithm such that in the process you want to modify, produce G prime equal to G complement and K prime equal to K. So you produce G complement and G prime and K prime by this method, and then you feed into the clique solver. Now by the construction, if the clique solver says yes, that means G prime had a clique of size K prime, right? G prime had a clique of size K prime is equal to K, so G prime had a clique of size K, that means G had an independent set of size K. So if the clique solver tells me yes, then I can actually answer yes for the independent set solver as well. And if the clique solver says no, then we can say no for the independent set solver as well. Okay? So this is clearly relating the clique solving problem to the independent set solving problem, right? So this is the kind of relation that we want to look for. We actually want to look for, suppose hypothetically you have an algorithm for solving clique, right? Whatever running time. Let's say that for simplicity, let's say that it's a order n square algorithm. Then what would be the running time for the independent set solver? Order n square for that box, and then the time required for converting gk to g prime k prime. That also is n square, because we just complement the adjacency matrix. You take the adjacency matrix of G and complement it and write it output. So that also is right. And so totally it will be like order n square again. So that's how the connections work, right? So with this we will say this process, that ellipse shape that we drew here, that has the formal name as what is called a reduction from independent set to clique problem.
So basically this means that any instance of independent set can be converted into an instance of the
clique problem, and if you have a clique solver for it, you can actually use that for it. How about the other way around? It is the same, right? You can see immediately related, you can actually work the other way around too. So the same thing, in fact same idea can be used to show that clique also reduces. So let me introduce this notation, clique less than or equal to in set. Meaning that if you solve independent set problem, then clique is easier, or clique is a lesser problem, less than or equal to, right? That notation is just that, but that's so independent set to clique and clique to independent. So they actually are quite close cousin problems, that's what it means. Although we talked about them in different domains and so on.
Why is the inequality clique less than equal to independent set? Why could not it be other way around?
So the previous line says that independent set is less than or equal to clique as well. Then together we would write it as independent set is equivalent to clique, right? So that's so if both of them are one way or the other, both reduces to one another, then they'll be equivalent. There may be cases where they are not. We'll actually talk about it in 1 minute, right? Okay, so what we just showed is that the clique to independent set, they are quite cousins of each other. Clique reduces to independent set and independent set reduces to clique. That means if you have an algorithm which runs in polynomial time for independent set, you can use that to design an algorithm for running in polynomial time for independent set, for clique as well. So either they fall together to P, right, or they stand separate. So that's what So separate from P together. So they are always going to be together. The same idea is what we are going to demonstrate for independent set to vertex cover. Oops. Right? So I'll just write the idea. I won't write the box and so on. But let's try to understand the connection between these two problems. So the independent set and vertex cover. Okay. So suppose that I have a graph G, okay, and there is an independent set of size. There is an independent set, let me erase this, of size k, size of V prime is k. What does it mean to say that V prime is an independent set? None of the vertices inside V prime have an edge among them, right? That means where are all the edges in the graph? All the edges in the graph are either from V prime to outside or outside V prime altogether, right? Now here is a vertex cover. Can you see a vertex cover for the graph now? So you just take the vertices in the outside. If you take the vertices in the outside, you would have hit every edge in the graph. Correct, no? Because every edge has either one endpoint outside or both endpoints outside. No edge have both endpoints inside because V prime is an independent set. So hence here is a vertex cover. So there is a vertex. So if V prime is independent set is an independent set, then V minus V prime, so forms a vertex cover. That means that G has an independent set of size k if and only if G has a vertex cover of size n minus k. Right? Now you see that if somebody gives you an algorithm to solve vertex cover problem, you can use that to actually check whether there is an independent set of size k by providing it the k for the vertex cover should be n minus k of the original parameter. So if there is some, I haven't written it in the box form, but I hope you can offline you can think about writing that box form and connecting them, right? So that means that in the previous picture, I'm going to go back to the previous picture. The same idea can actually be used in both ways. So independent set and vertex cover are also close to each other, connection. So that means that by transitivity, by connecting them again, vertex cover and clique would be connected and so on. So all of them three together either fall together to P or they will be separate from P together. It will never happen that vertex cover is in P and the other two stands out. Okay. So that's the connection between these three problems. Does it stop there? No, actually it doesn't. There are many other problems that are going to be there, right? Are they all related to each other? That's a natural question that we would want to ask. And in fact, if I want to try and design an algorithm for a problem in NP to design to put it in P, if I want to try and design an algorithm for P, whom would you choose? Which problem would you choose? So here is a natural thought. If I want to design an algorithm for a problem in P, I probably would aim high to start with and say that I want the hardest problem in NP and I want to put that person in P. In what sense is it hardest? For example, if I put clique, I know that independent set also will fall. Similarly, I would want to understand if there is a problem in this class which actually is everyone else should reduce to it, right? Everyone else should reduce to it. Such a hardest problem in NP is what I would look for to actually try to put it inside P.
So that means if the hardest problem in an algorithm in P, then all of the problems in NP will fall down to P, and that will settle this question, right? We'll say that NP is equal to P in that case. So there is a motivation to understand if there is a hardest problem in NP. It is not clear a priori, right? How do you show that there is a problem that's hardest in NP?
there is actually a challenge there, right? Because we can only talk about clique independent set vertex cover. There could be other several problems here. Let's go back to how we defined NP. How did we define NP?
Yes.
Any problem that has
Easy yes.
that yes instance of the problem has an easily verifiable short certificate and no instance doesn't. So that is what we talked about as NP. So you have to start with any problem that has that property and try to reduce it to our hard problem. Then you can say that what we are talking about is a hard problem, a hardest problem in NP, and then attack that question. So let me write down this as a sentence. We won't get into the details of this, but let me write down this as a sentence. So if there is a problem in A, there is a problem A such that every problem in B in NP, B reduces to A, then we call A to be NP hard. Okay, and 2, in addition, if A is also in NP, then we call it NP-complete. Okay, so NP-complete, NP-hard. These are two terms that I am throwing in now. Yeah.
Hardest problem, then every problem would become the hardest problem, as every problem would be reduced to that. So,
correct. That the one to which everyone reduces is the hardest problem, not everyone else.
no,
Huh.
every problem reduces to some problem.
So let's say that this is the NP.
Yeah.
Okay, and there is a problem A to which everyone reduces to.
Yeah.
But one way arrow doesn't mean that the other way arrow also exists.
Yeah.
Correct. So if I pull in A to P, then all these problems to which had arrows to A, which reduces to A, will also fall into P. Whereas if let's say I had a problem C here, and C reduces to A, and I pull in C to the polynomial time, that doesn't mean that A will fall into P. When I draw an arrow C to A, what it means that if I have a program solving A, I will have a program solving C, not the other way around. Right? It so happens that in our example, arrows always went back and forth. They were close cousins of each other. There are actually cases where that doesn't happen. Right?
What if such key doesn't exist?
So in NP, we already showed there are 3 problems. In fact, there are many more problems. So what do you mean by C doesn't exist? I didn't. Oh, A doesn't exist. Okay, good question. Why would A exist, right? In fact, so that is what the next theorem which we are going to state. So this is called the Cook-Levin Theorem. So it may not exist. That's clear. You are very right. This is called the Cook-Levin Theorem. That where he showed that such an A exists, not just an exists. He will actually specify a particular problem, right? Which is NP-complete. Yeah.
By the way, so this NP-complete problem is the hardest problem in NP.
In NP, correct. So we actually would want to attack them if you want to show that NP is contained in P. So Cook-Levin theorem says that, in fact, I will not write it in the original form. I will just say that clique is NP-complete. Meaning that clique is already in NP, we know that. What this says is that every other problem will reduce to clique, not just those 3 problems. Everyone else actually reduces to clique, right? And that's what the importance of, so it does exist. And if clique is NP-complete, actually its cousin problems are also NP-complete, because independent set is actually exactly the same difficulty as clique, right? So independent set is NP-complete, vertex cover is NP-complete. So you have a picture now. Let me draw the picture now. So this is P, and this is NP, and there is actually a set of problems inside NP which are NP-complete, okay, which everyone reduces to them. Everyone reduces to them. Okay, clique is here, independent set is here, vertex cover is here. There are many more interesting problems that are there. We do not know if any of them are NP.
Sir, is minimum circuit problem NP-complete?
No, right? Because it's not known to be in NP. because we drew minimum circuit outside NP. Right? We do not know. So if you remember this diagram, min circuit was here. One of the requirements for minimum circuit being NP complete, it should be inside NP. But it is NP hard, meaning that it's actually harder than all these problems. Everyone can reduce to min circuit problem. So if you put min circuit in P, then also all these problems will fall. That's also true, but that's not NP complete, it is NP hard. It's harder than everyone in NP, but it's not inside NP. So it's not NP complete as such. Okay?
By the way, I was simply just curious that is monotonic circuit easier for something that can make the
For the minimum circuit problem?
yeah.
No, not known. Yeah. Okay. So let me comment about this intersection between these two classes. The moment if we show that there is a common problem between these two, what is the consequence? Every problem will fall down, because what is the peculiarity of this set? Everyone in NP reduces to the NP complete problem. If there is one NP complete problem which is also in P, that means that the entire NP will fall down to P. So that means that the open question NP versus P is actually closely related to whether these two are actually, is this drawing correct? We don't know that. This drawing is from what we try to define it. We do not know whether this drawing is correct. So the set of questions around this is what the area studies in detail. Okay, so I'll stop the lecture.